right, thank you. Hopefully you all can hear me pretty good. All right. I'm going to be talking about moving off policy and resilience to your internal developer platforms. I'm kind of curious, by show of hands, how many people are working on or use an internal developer platform at the company where they're at? Okay, a few. So let's see, can we get this going? Yeah, all right. So we introduced me, that's all good. I work for a company called Solo.io. Solo is based here in Boston, actually, in Cambridge. I don't live in Cambridge, I live in Phoenix. So I'm happy to be here in Boston. It's probably going to be 113 in Phoenix today. Much better here. But at Solo, we work on open source cloud networking technologies. We are very involved in the Istio project, the founders and the lead contributors, and we lead the innovation and a lot of stuff that's happening in the Istio project, as well as some of the surrounding periphery projects, some of which we'll be talking about today. And the clicker is not working. All right. There we go. All right. As you know, digital experiences are kind of how we do things today when we get around. I flew here to Boston. I got on my phone. I booked travel. How many of you remember what it was like before that? You had to pick up a phone call. Pick up a phone and make a call to a travel agent to book your flights, to book your hotel. You had to call some random number to book a taxi, and hopefully that taxi showed up. Digital experience has made our lives a lot easier today. We save a lot more time, and that's extremely valuable. APIs and services underpin the apps on our phones and the digital experiences that we use. And these organizations, these businesses, they see APIs and services and the infrastructure to get those live and into production as being driving a lot of business value, being differentiating. And the developers and the time that they put into building out these new services, new capabilities, are extremely valuable. The challenge with that is getting code and getting these changes into production. And I work with organizations that experience this all the time. A big part of that is the siloed nature of their organizations. They built their code, they staged it, get it ready. You got to now make changes to your API management system, to your load balancers, to your firewalls, et cetera. And the way these organizations have been structured aren't conducive to being able to do this very quickly. They've made decisions in their own silos. The integrations between those silos are very complex and brittle and expensive. And if you want to get anything done, what do? You open tickets, and you sit and you wait. And hopefully these teams will go off and go to their, these UIs and point and click and these manual steps to get things done, make the changes, and then eventually you can get things into production. So that's why you're probably seeing, and we see this, we work, like I said, very closely with these organizations that are going down this path of building platform engineering teams, building internal developer platforms to try to bridge and work across these silos, to try to build APIs, internal APIs to support automation so that they can build the tools, the workflows, the UIs, the experiences for their developers to be able to self-service and build, deploy their code into production as quickly and safely as possible. So they build these paved paths or these golden paths. And the platform engineering team and the platform itself is intended to be a business value accelerator. We want to improve the ability to get these APIs and these services out into production faster. We want to improve efficiencies. We want to maintain or improve compliance. Do things like reduce costs and lock in and so on. So this is a trend that we're seeing. How many people have built their own house? Kind of curious. Raise hands. Nice. Okay. Awesome. It's not easy. It's not something I would want to do. I've lived through a remodel. I don't want to do that again. But when you build a house, you don't start with laying electrical wire or putting in doors, right? You start with the foundation. You start building walls and a roof and so on. I think about internal developer portals like a house. It's a foundation, a platform on which you can get value out of it, build value, do things, work from home, raise a family, raise your pets, sleep comfortably, et cetera, and then be productive the next day. Internal developer platforms lay that foundation so developers can actually get their work done and be efficient. And the organizations that we work with are trying to improve their cross-team and silo communications. They're adopting new technologies like containers and cloud and building automations, CI/CD, putting in observability tools and so on. But there is something missing, and it is fairly glaring when we start working with them. Anybody care to take a guess what's missing from this list right here? No guesses? There's no right or wrong. What is it? Security is very important. Yep, absolutely. These services need to communicate with each other. Gregor Hoppe just released a book on platform engineering, platform strategy, and he identifies the needs for a platform, internal developer platform, and he calls it the four-leaf clover of engineering productivity. And delivery pipeline, monitoring operations, the runtime, compute, all that stuff, obviously very important, but you need to solve the communication problem. You need to solve the networking problem. And when we work with these organizations, we see this as, they built the foundations, they put the containers and Lambda and whatever else they're going to use, CI/CD, and they still have challenges getting code out into production. T-Mobile did an internal review of why is it taking weeks to get changes out into production, even though they've adopted these modern platforms. You can go and take a look at this talk where Joe Searcy goes into the details of that research and how they built their platforms to solve some of this. But they found that 25% of developers' time was spent on these non-functional requirements like routing, like security, some reliability stuff, and that they would open these tickets, try to get changes into production, and sit and wait. They would find that for production issues and outages and stuff that they had, 75%, 3/4 of those were caused by network misconfigurations. So if you've not addressed the networking and communication parts of your platform, you're still relying on some of the existing ways that don't quite fit the way you're building your cloud platforms, then your house is not finished. It's probably not a good idea to live in it. Some of the outdated assumptions that we run into, especially in the networking and API management space, is those around how you specify policy. So oftentimes this is implemented as firewalls and firewall rules and so on in these organizations. Things like, well, we're going to write our policy in terms of network location or network identity, things like IP addresses. And if something in the network changes, those policies become invalidated. Right? In this very simple case, we're saying this IP address can talk to this IP address. But what we really mean is service A can talk to service B. But if we start adding more workloads to the node that has service B, now we have this drift in policy. Service A can now talk to service C also because it's deployed on this IP address. But that's not really what we intended. Now, there's a very simplistic example, and these can get very complicated. But as the network changes, the workloads change and shift and move, you get this policy bit rot, just like you do with code. Another one that frequently pops up in the cloud space is these IP addresses are ephemeral. They, a host or a VM can go down and come back up and potentially come up with a new IP address. Or in Kubernetes, pods will recycle and have new IP addresses. And policies written in terms of those IP addresses are going to be invalidated as IPs get reassigned. Another one that we see is these organizations. They've implemented these API management systems to solve things for rate limiting and security and observability and so on. Originally intended for external APIs, now they're using them for internal APIs. And now to go make changes and get changes into production, you have to open tickets. And it's not uncommon that we see organizations saying it takes weeks, a couple weeks, to make changes to their load balancers, to their API management systems, and so on. So from a workflow standpoint, this causes bottlenecks. From a technology standpoint, these systems are not that well, the tendency model we see where certain APIs misbehaving will impact other APIs and so on. So from a technology standpoint, there's bottlenecks and issues there as well. And they can force unnatural traffic patterns. We've seen this many times where workloads in a single cluster want to communicate with each other. One API calls another. But to do that, they have to be forced out of the cluster, out through load balancers, out into some centralized API gateway, then through the gateway, back down through load balancers, eventually back into the cluster. These workloads might have been deployed on the same host. But for them to get the policies and authentication, authorization, observability, they have to go through these unnatural patterns. One thing that I pointed out was in the in T-Mobile is that developers sometimes they're like, I don't want to open tickets. I don't want to deal with all this infrastructure stuff. I'll just write it in my code. I'll just write the security stuff, the load balancing. I'll just write the service discovery stuff. I just put it into my code. That gets expensive, doing across different languages, different frameworks, making the business logic all convoluted because now you have this networking code in there. And from a security standpoint, it's not that easy to get right. Using tokens, using keys, usernames, passwords, putting that all over the environment. It's very easy to have a mistake creep in and have a security vulnerability. I blogged about this in much more detail, especially around using JOT tokens as service identity. Using JOT tokens, all that stuff for user identity, you log in, OAuth, whatever, that's all good. But for service-to-service communication and workload identity, there's a lot of things that can go wrong there. So what we need for modern networking is something that's not highly centralized. So we still need a distributed implementation. We need to tie it into our existing infrastructure as code, GitOps style workflows and automation. We want standard interfaces to be able to integrate with other pieces. There's not going to be one technology that does everything, so we need standard interfaces. And we need to do the networking stuff that we've been doing already. Traffic routing, load balancing, authentication, authorization, rate limiting, observability. We still need those capabilities. And if you don't have those, and if you've built your platform and you don't have those capabilities, then your house is unfinished. Like I said, I remodeled my house probably about 5 years ago now. It was a bit of a pain. But eventually we did reinstall new pipes, new electrical ACs, especially in Phoenix right now. You need those pieces. To live comfortably in your house, you need those pieces. And the analogy there is, the locks on the doors are like the authentication authorization for specific requests, for every request between services. You need load balancing, retries, timeouts, circuit breaking, zone-aware load balancing, things like telemetry collection, distributed tracing, logging, and then, like I said, integrating with other parts of the systems. Maybe you have a policy engine like OPA or Caverno or something, or your own homegrown one. Maybe you have your own existing API gateway, and you need to integrate with that as well. So we need nice standard interfaces, just like when you're building a house, to assemble these components. And it needs to work for all the applications in your environment, regardless of what language, regardless of what framework they're using. We don't want the developers to kind of go off and re-implement this themselves. And so that's where things like a service mesh come into the picture. Something like Istio, which has been around, I've been working on it for about 7.5 years now. it comes into the picture to solve this problem, transparently enabling things like MTLS, mutual authentication, telemetry collection, distributed tracing, and traffic control. Now, Istio's been out for a little bit. I'm kind of curious, anybody using Istio in here in this room? We got one. Istio has been out for a bit and is traditionally been implemented by deploying proxies next to the instances of your workloads. So if it's a Java app, next to your JVM. If it's a Python app, the actual process that runs the Python code. And if it's in Kubernetes, actually inside the pod. But deploying, getting this infrastructure-y stuff into your applications creates this coupling and friction. First of all, how do you onboard? How do you get applications on? Well, now you have to inject this thing into it. But if you already have other sidecars, how do those play nicely together? How do you do upgrades? You got to restart all your apps because you got a new sidecar, et cetera, et cetera. And then there's the performance, there's the overhead. Sidecars were a necessary evil to implement this type of functionality. But this is the last that I'm going to talk about sidecars. We're going to talk more about the functionality of the service mesh. And we'll dig into a little bit how we implement this functionality without using sidecars. In September 22, I think we announced publicly in the Istio community an implementation of Istio that doesn't use sidecars. And in May, actually just a month ago or so, we've finally got it to the point where it is now in a state where it's usable in production. And we have people using it in production already. Let me just show you a quick demo, what that looks like. In my demo app here, am I logged in? Yeah, I'm logged in. In my demo app, hopefully y'all can see this reasonably okay with the light. Yeah? We have 3 apps in 3 different namespaces. We have Web API, we have recommendation, and we have purchase history. If I go into Web API, you'll see we have an app running there. This signifies the Web API team, different teams across the Kubernetes cluster. We don't have Istio, we don't have any sidecars or anything installed. And in recommendation looks the same. Purchase history actually has 2 different versions, which we'll use later in the demo to illustrate routing. But at the moment, let's come here and let's there's in the default namespace there's a sleep app that we'll use as a client, at least in this next step, and HTTP bin, another sample application. So Web API calls workload, Web API calls recommendation, recommendation calls purchase history. So if we call Web API through the sleep app, we'll see that indeed Web API calls recommendation, and recommendation calls purchase history here. So we're going to come over here and we're going to actually start our demo. What we're going to do is we're going to install Istio. Now this will take a second, but you'll notice in the command here, I'm going to use the new ambient profile. So this is going to install Istio's ingress gateway, which is just a default, it's Envoy proxy for getting traffic into the mesh or into the cluster. It's going to install the Istio control plane, Istio-D, if anybody's familiar with that. And then it's going to install a couple components that will enable us to do the sidecarless implementation of Istio. And I'll talk a little bit more about what those components are. As part of the installation, I want to install Grafana. I want to install some observability apps so that we can see some of the tracing. And we'll give it a second. We'll take a look. You can see here in the namespace list, Istio system now appears. I click into there. We'll see things are still coming up. Grafana's up. Istio-D right here, the control plane, the ingress gateway, and a few other components. Z-tunnel, and then the Chiali. We'll wait for Chiali to come up. We'll use Chiali here in a second. All right. Now, the first step we're going to do is we want traffic to get into the mesh. We want it to come in through the Istio ingress gateway. So we're going to apply some policies, some routing policies to allow traffic in through the ingress gateway. The ingress gateway is exposed on this external IP address. So once we apply this, this policy, we'll end up using that IP address to make the call. The routing policy is very simple. Match on a particular host, Istio and action.io, and then route it to Web API. And like I said, traffic comes in. Web API calls recommendation, which calls purchase history. So we'll do that. Now, if we actually make the call through that IP address, back here, you can see that you get the correct response, and it goes through the Istio ingress gateway. Now, what we're going to do is we're going to add our Web API recommendation and purchase history to the mesh, and we're going to do that by labeling the namespace, each respective namespace. In this case, we'll also do the default namespace. There's some sample apps there. We'll label the recommendation, and then the last one here, purchase history. This is a live demo, by the way. I'm just have it automatically typing for me. And that's it. Our apps are now part of the service mesh. There is no sidecar running here, as you can see. This is Istio ambient mode. Now, if we come over here to the Achilles console, yeah, let's go ahead and port forward that. All right, just do some port forwarding and get the Achilles console to come up. We don't have much traffic going through here, so let's get some traffic. Let's call. We'll send about, I think it's 250 requests through the gateway, and that's good. We should take a look at our workloads that we have deployed here. Web API, recommendation, and purchase history. And we see that Achilles recognizes the workloads here. If we look at the Istio config, we can see the Istio config that's been deployed. Just not much going on really, just allowing traffic in through the ingress gateway. And then lastly, if we click on the traffic graph, actually I was hoping it would show up the other way. It does not. What we should see is, we still don't see the traffic. Give it one more run to generate the metrics. The metrics end up going into Prometheus. Kali scrapes Prometheus, and it should show the traffic flow here. There we go. We can see Web API calls recommendation, which calls purchase history. We can also see the, let's see if I can get some animations here. Service traffic animation. What we also see is through these the lines between the different services is we see this lock. If I click on these locks and look off to the right-hand side here, we see that Istio is enabled. We have MTLS enabled between these services. The services are using spiffy workload identity, which we'll talk about in a second. But we've done nothing more than just label the namespaces. We've already got the services into the mesh. They're protected by MTLS, so their traffic's encrypted, and we have workload identity assigned here. That's pretty good for just labeling a namespace. So the way Istio ambient works, just at a high level, I'll leave you with some links at the end to go into a little bit more detail. But the way that it works is Istio ambient deploys an agent to each of the nodes in the cluster, and this agent binds directly into the pod's network namespace. So what that means is traffic will leave the pod, but Istio ambient will have already done some stuff to that traffic. So the Z-tunnel will have done that. And in this case, what it's doing is matching an MTLS certificate to that pod and enabling mutual TLS. So once the traffic leaves the pod, it is already encrypted. It is already participating in MTLS. It's being tunneled to whatever the destination is, and that obviously that other side will participate in the MTLS as well. I'm certain I'm going to get this question, so I'll draw a picture about exactly what the Z-tunnel is doing. Traffic is not going from the pod to the Z-tunnel. It is leaving the pod already having been encrypted by the Z-tunnel. The ports are opened up inside of the network namespace of the pod. All right, so we get the same behavior that we do with sidecars. Sidecars actually deployed into the pod, but without deploying sidecars. Now that's great for layer 4 connections, MTLS, but what about layer 7? Things like request-based routing or retrying of a request that failed, or JOT, validation and authentication and authorization. For that, what Istio Ambient does is it injects a layer 7 proxy that we call the waypoint proxy into the traffic path. Since we already control it with the Z-tunnel, if there are layer 7 policies, we can route it to a layer 7 proxy. Now that layer 7 proxy, we don't want to treat that as some big centralized gateway. What we want to do is have better tenancy for it. And so in a Kubernetes world, the default is to deploy a waypoint proxy per namespace. So for each namespace, you'll have your own layer 7 proxy. If you need more fine-grained tenancy, what you can do is deploy a waypoint proxy per service identity or service account in Kubernetes, for example. So you can control the tenancy of these layer 7 proxies. You don't get these big, centralized API gateways, but you do have API gateway functionality. And so in these proxies that now live in the network somewhere, they can be scaled, right? If you want high availability, you scale multiple of these waypoint proxies, and you can size the proxies more appropriately to the traffic that is destined, in this case, for pod B. The sidecar approach, you just scale up more pod Bs, but then you get more sidecars, more proxies. We've gone into a lot of performance analysis, resource cost analysis, comparing it to sidecar, comparing it to other service meshes. This was a fairly large deployment. I think we were doing, I forgot the number of services, but it was in the order of 110, 112,000 requests per second through this environment and setup. And we took measurements of the baseline, what ambient looks like, what other service meshes look like, what the sidecar looks like for comparison. And because of this optimization, where if you just need MTLS, you don't have to inject sidecars, you don't have to do anything, this network path becomes extremely fast. It's just layer 4. If you need to use layer 7 capabilities and inject the waypoint, this also ends up being faster than the sidecar, because we're processing HTTP only one time. Sidecar does it twice, once on each side. And the network hop that you take to get to the waypoint, the cost of that we've seen in our performance testing is lower than having the sidecars perform the HTTP parsing, all the stuff that they need to do. So ambient ends up being simpler to onboard, simpler to upgrade and maintain, especially for security patches and all kinds of stuff that you have to do. You don't have to reserve, it's a fraction of the resources that need to be reserved for CPU and memory to run sidecars, because you don't run sidecars. Performance is improved, especially in the layer 4 only cases, and actually security gets a slight improvement as well. But I'll leave you with this link here. Lynn Sun and I wrote a book, and goes into a little bit more detail about Istio Ambient. Go ahead and take a look at the istio.io website. Istio Ambient, like I said, just became available for production usage. It will eventually become the default data plane. It's not right now. Sidecars won't go away, but that's the path that we're on with Istio. All right. Let's talk in more detail about auth, policy, and resilience, and how moving that to the platform makes a lot more sense, drives down costs, and so on. We'll look at a few examples. One is Trust Bank. The QR code up there goes to the presentation that they gave at AWS reInvent. And I'm going to use public references so that you can go, if you're interested, to look them up. But Trust Bank was this new digital bank that was starting up as a joint venture between a bunch of other big banks in Singapore. And they went from nothing to 1 million users in a very, very short amount of time. They were cloud first. They built on EKS and AWS. But for their networking components, they used Istio. The problems that they were trying to solve were around compliance, security, encrypted traffic. Things like they started off with a handful of clusters. They wanted to add more clusters and deploy workloads into more clusters, but they didn't want downtime for their apps. They wanted to be able to move apps to different clusters, different regions. They started to encounter regulatory concern around data, gravity, and that kind of stuff as well. They needed to be able to control the routing. But from a authentication and authorization standpoint, they didn't want to force everything through these centralized systems. They needed a decentralized networking approach, and that's where Istio came into the picture. So we talked a little bit about what the existing assumptions and existing approach to defining policy looks like with IP addresses and firewalls and so on. But what we want to solve is the workload, service-to-service communication and authentication problem. How does service B know that it actually is service A that's calling it? And that's where a specification called SPIFFE comes into the picture. So SPIFFE is a spec for workload identity and how to get those credentials that prove you are a certain workload. So it specifies what they call a verifiable identity document, SPIFFE verifiable identity document, that is usually in the form of an X509 certificate. It doesn't have to be. It can be other formats, but X509 is a common one. And then workflows for how does a workload get that document? How does service A prove that it is service A? Because what we want is, and the way that it works, is service A will request its verifiable identity document, an X509 cert, that says I'm service A. And the SPIFFE workflow and the implementations behind the scenes will then go and say, okay, I need proof that you're service A. I'm going to go do a background check, basically. I'm going to go attest that you are indeed service A. I'm going to go check the machine that you're running on. I'm going to check the context that you're running in. I'm going to check the attributes assigned to you. And if that all lines up and you really are service A, then I'll give you this document. And now that X509 document is presented by service A to service B saying, hey, I am service A. And service B can look at it and check the authenticity of that document. And a common way to do that is TLS and MTLS. This is where Istio comes into the picture. Right? Istio can automate the MTLS connection transparently for your applications. And Istio does implement SPIFFE, so they work very nicely together. So now, if workload A is workload A, is provable, cryptographically provable, and it's talking with workload B, and we know these identities are durable, we can write policy about what services are allowed to talk with which other services. And in regulated environments, this type of policy is extremely important. And Istio allows you to write this type of policy in terms of workload identity in a declarative format that can be automated, fit into your GitOps workflows and pipelines and so on. I'm going to jump into a quick demo that shows what that looks like. So again, we have web API calls recommendation, which calls purchase history. The first thing that we're going to do is we're going to lock down all communication in the mesh. We're going to deny all. In a realistic world, you can't just come in and shut off all traffic. Istio does make it, you can iterate and incrementally add these authorization policies and eventually get to a zero trust environment where you deny all. But for this demo, we'll start with just lock down all traffic. The only thing we will allow is people can call the ingress gateway. So we'll apply this authorization policy, and we're going to try to make a call to the gateway. And by the error message, you can't really tell, but it makes it to the gateway, but that gateway says, oh, I can't route this to Web API. I can't call. The traffic can't proceed in the mesh right now. Everything's denied. So what we want to do is adjust the policy. We want to allow the ingress gateway to call Web API. And using an Istio authorization policy, what we're going to do is do that based on identity, not what cluster this thing's running on, or what IP address this thing's running on, or what pod it is. We're going to do it based on workload identity, the spiffy workload identity that I just described. And we're going to allow that traffic for Web API. So if we allow it, and now make a call, we should see traffic go from ingress gateway to Web API, but not surprisingly, the rest of the traffic is still disallowed. So let's go ahead and add that. We'll add the policies to allow traffic between the rest of the chain of the services. And now if I make that call through the gateway, everything proceeds. The calls work again. But from the sleep app, which is in the default namespace, I shouldn't be able to call Web API. Ingress gateway can, other apps cannot. And let's take a look. I try to call it, and that does not work, which is what we expect. Now, so far, this has been mutual authentication and policy enforcement based on identity, but we can be even more fine-grained than that. We can specify policies about what services can call what other services, and specific endpoints, specific HTTP verbs that they can call, specific headers that have to be present or not present. And we see a little bit of that in this next part. I want to allow the sleep service to call HTTP bin, but only at /headers, and only if this X test me header is present. Right? So now we're looking at layer 7. We're looking at the request itself, the details of the request, and we're going to build some authorization policies, in terms of some of those details. So now if I add this, actually, before we do that, in Istio ambient, if you're going to do anything with layer 7, you need that waypoint proxy that I mentioned. This is that layer 7 proxy that gets injected into the network path. And those get deployed in Istio ambient by default, 1 per namespace. So I just created this, I don't know how well you can see that, this waypoint proxy. If I come into the default namespace, we can see sleep, which calls HTTP bin, but now we've included this new waypoint proxy. And we're going to apply that policy to allow sleep to call HTTP bin. And now when we call it, it won't work if we call /IP. That was not whitelisted. That was not part of our authorizations. But if we call it with the right header on the right path, in this case, the call will go through. So we get very fine-grained layer 7 authorization policies declaratively with Istio. All right. Yeah, we got to that. The last section here goes into a little bit more of the traffic control and traffic routing. Intuit has given a number of presentations on how they've built their platform using Istio, multi-cluster, and one of their big use cases is when they deploy a service and they make an upgrade, they deploy that the new version of that service into a different namespace. And they might move it into a different cluster. And so what they need is globally aware routing. When we deploy a new service, we don't want to take an outage. Another company gave a similar talk, but in their motivation, their reasons for needing that global routing and failover, et cetera, were for data gravity and compliance reasons. GDPR, you have to have your data in a certain region, and if you want to access it, you have to go through and to that region. Istio is really good at controlling traffic, both load balancing, being zonal aware, being multi-cluster aware, and routing across multiple clusters. And we can also implement things like, when we have traffic control down to the level of a request, we can also implement things like resilience. So we can be resilient in terms of load balancing, we can be smart and cost optimized in terms of load balancing, but we can also do things like timeouts, retries, and circuit breaking, and offload that from the app developers having to worry about that. Like I mentioned, globally aware routing. If a service is talking to a service in one cluster, but the destination service fails, we can fail over to a different cluster transparently, and still have MTLS, still have our authorization policies enforced, and do it in a smart way. We're not going to automatically fail out to a different region. We would try to prefer locality. We'll try to prefer zonal affinity, and then fail out to a different region as necessary. I mentioned the circuit breaking. If I'm making a call to a service and it's misbehaving, stop calling it, or at least for a period of time, back off, right? And then slowly try to call back into it. All right, this is the last part of the demo. Purchase history has two deployments, a V1 and a V2. And if I call that, we see in this instance we had a response from purchase history V2. If I call it again, also V2 it looks like. We should see it load balance. There we go. There's a V1, V2. So it'll load balance about 50%. This is what Kubernetes does automatically out of the box. So what we want to do is force all the traffic to V1, right? That'll be the production available version. We'll write a default routing rule here that says 100% of the traffic should go to V1, 0% should go to V2. However, we might want to introduce V2 as a canary. We want to be very specific and fine-grained about what services can call the V2 version. And to do that, we'll add a match that looks for a specific header, and if it has this header, then we'll route it to V2. Again, we're doing Istio layer 7 stuff, so we're going to add a waypoint proxy into the purchase history namespace. We can see that down here at the bottom, kind of. Now, let's go ahead and apply that routing rule. And now let's start making calls. So if I make a call to, well, actually we have deny all authorization policy. We have to enable that for the waypoint. Now what we're going to do is call the services 15 times. We're going to use jQuery to kind of pull out the bodies. We see 15 times in a row. We get the call ends up going to purchase history V1. And if I want to do the canary part, you can't see it, but at the bottom here, we called the services with this header, which triggers that match in the routing and routes it to purchase history V2. What if purchase history is misbehaving? What if it's returning errors? I just deployed a version of purchase history that half the time is going to return 500 errors, right? As we can see here, we call it a handful of times. With Istio, like I said, we can do timeouts, retries, circuit breaking, type thing. So let's take a look at a retry policy that we will want to add here. So if you're calling V1, if you're calling purchase history V1, down here on the bottom, you can see I want to implement retries. I'll retry up to 3 times on 500 type errors. So now if I apply this and then make calls, we should see every time the calls succeed. I mean, they might be failing. We can check the retry metrics. They might be failing in the background, but the retries are kicking in and making it so that the call succeeds eventually. All right. Well, let's tie it all together. Istio in general provides a lot of capabilities for fine-grained modern networking. Istio and solving this networking challenge should be part of your modern internal developer platform. You can see that here in the stack. This is sort of how it lines up in block diagrams. One thing I will say, and you'll notice here, Istio is buried down here in the bottom of the stack, right? This is networking. Application developers shouldn't have to know about Istio. The APIs, the workflows, the interfaces, the experiences that you build for your developer platform should enable things like maybe doing a canary release or publishing telemetry and metrics to Grafana dashboards and so on so that they can see what's happening with their services. Things like security policy are probably not driven by developers, but I mean, if your workflow includes that, then your workflow can generate those authorization policies and the details around what services can call which other services or API endpoints. And so all of that stuff should be automated away. They shouldn't have to know about this. And from a platform, like what are the business outcomes of the platform? Originally, I mentioned you want to increase business value, you want to increase compliance, and you want to make things more efficient and reduce costs. There's a lot of text here. I'll just quickly talk about what it is. But from a value standpoint, your code on the developer's laptop or in CI does nothing unless it gets into production. You can't get value out of that. And tools like Istio implementing something like this allows you to do more safe releases, canaries, blue-green deployments. A lot of network telemetry can be pulled back, distributed tracing, and so on. And you can make those decisions about whether to go forward and so on. I'm getting the stop signal here. I will leave this right here. The slides are online. You can go back. Reach out anytime if there are any questions. Apologize I didn't leave time for questions live here, but thank you all for attending, and thank you, InfoQ, for having me here.